Hey there. Good afternoon by now, everyone. Good to see you here, and especially warm welcome to today's speaker, Dr. Marty Ralph, who is the director of the Center for Western Weather and Water Extremes, which is part of Scripps out in San Diego. Marty and I met many years ago, so many years ago that we were both, when we were chatting prior to the talk, we were trying to figure out when and where it was. It was in Boulder for sure, and probably at NOAA is what I was thinking. So Marty is a hydrometeorologist with a Ph.D., I think, from UCLA, but you spent a good chunk of your career in Boulder at Eswell, where you eventually became a division director. And at the same time, you were a program manager in NOAA and for USWRP, and another initiative whose name I've forgotten in the meantime, but USWRP I knew quite well back in the day when I was Joint Center Director. You then moved to Scripps and created this center, CW3E, out of nothing, basically. You grew it from zero to the size where it is now, with, as I understand it, around 100 people, all soft-funded. So we were commiserating or comparing notes on how you do that. What are the ins and outs and the ups and downs of that? What you are focusing on, both in your career and in your center, is water, which is, of course, incredibly important for life and for economies and around the world. And there's a lot of stuff happening with water now. You can call it climate change, or as you told me, you sometimes call it water change, because there are political circles in which that is a more palatable term than climate change. Whatever you want to call it, things are happening with water. We are sometimes getting more of it, sometimes less of it, but we are getting or not getting water at inopportune times and in inopportune places, and that is really what you are studying. So your center says something. Its name says something about Western weather and water extremes, and that reflects the fact that in the Southwest, water is sometimes a scarce commodity, and when it is not, there's really too much of it. So that's what you're going to be. One of the phenomena that you define or that sort of sets the boundary conditions for water management in the Southwest is atmospheric rivers. And the title of the talk is Atmospheric Rivers from Science to Solutions. So we look forward to hearing what you have to say about that.
Yes, John.
Good afternoon. Nice to see some old familiar faces, and welcome to those online. It's morning on the West Coast, and I imagine a few folks might be chiming in from there, signing in from there. So yeah, thank you for the invitation to present at the seminar series here, and for the chance to be here. I was going to be in DC. Thought I'd come by in person and enjoy a chance to meet. Hadn't met ESSEC before, have never visited. Thought it'd be a good chance to learn more about what ESSEC is and how it operates, and learned a lot today already. So thanks for that. What I want to talk about today is really sort of an overview of a lot of work. So it'll be just sort of touching on a few things briefly, and a couple things a little more deeply. But it really hinges on the fact that fresh water is both a resource and a hazard. And I think for many of us, we realize it that way in our lives. And I want to share that through this theme through this talk. Oh, I need to use this thing. There we go. So I've got 4 sections for the talk: setting the stage, a little background-ish kind of thing, prediction and atmospheric river reconnaissance. FIRO is Forecast-Informed Reservoir Operations, so using forecasts to help operate reservoirs, which doesn't, in many of the reservoirs in the country, hasn't traditionally been allowed. And then, given in spirit of Earth System Science Interdisciplinary Center, a few broader topics I'll touch on at the end on Earth System Science. Well, first of all, when we think about water, and it comes from the precipitation, our annual precipitation varies a lot around the country. We have the deserts in the Southwest. I'm from Michigan originally. The it's wet there every season. And in the eastern U.S., those pink dots mean that the standard deviation of the annual precip is around 10% of the total precipitation. So it's sort of a small change from normal. But you get to the Great Plains. I lived in Colorado for 20 years. There, it's more like 20 to 30% variation from year to year of the average is the standard deviation is. You see those green and blue dots in the Southwest, that's where we get places where it's 50%. So in other words, there may be a place here like 40 inches a year, and standard deviation is plus or minus maybe 4 inches. Whereas in parts of California, it's plus or minus 20 inches where you have a 40-inch average. Imagine 1 year you go from 20 inches to 60 inches. It's also the breadbasket in many ways. It's a fruit basket, at least for much of the country. So agriculture is so dependent on those swings. The economy in the Southwest is incredibly dependent on these big swings from year to year in annual precipitation. So the storms that make that, the climate that makes it, really hinges on a few big storms, as the box here says. Oops, I got to do this. So what are those storms? Well, there's extratropical cyclones are the primary thing. The monsoon, the southwest monsoon is important as well, but it doesn't really produce that much in the way of water supply. It can produce flash flooding in small localized areas for the most part. The big floods and most of the precipitation comes in the cool season, and storms like this beautiful sort of a coiled spring version of a bomb cyclone, just beautiful phenomena, quite dangerous in some places. And we've spent a lot of time focusing on the cyclone center, and you can see that eye there in the middle. But I'm showing streamlines here, overlaid with the color fill of purplish colors that are water vapor content. And what you can see is the atmospheric river is greatly displaced from the center of the low. And it turns out we've spent in meteorology over a century really learning a lot about the low center and how to predict it well. But the fundamental challenge is you can get the low right, but you don't necessarily get the atmospheric river right, which means you're not going to get the precipitation or the runoff right. So we have focused, I have focused now for 20 years or so on this phenomena of atmospheric rivers. And here you see an example that on average are about 1,000 kilometers away from each other. I want to point out that the paper that really turned me onto this topic came in 1998 from Zhu and Newell. It defined the concept. There were a handful, 3 or 4 other papers around that time. Then the topic more or less died for several years. It wasn't popular or ran against standard sort of thinking. And I saw that paper and I saw the new data that I had started to use, and it was very clear to me this is a real phenomenon in the atmosphere. It warranted further attention, and henceforth, here we are. So here's an example of what we use now to define an atmospheric river. On the left side of the diagram is the integrated vapor transport. You take the horizontal wind times the water vapor at each level in the atmosphere, and then you add up that vertically. And that gives us basically the picture of the atmospheric river conditions. And I've shown on the right in this particular case, which was a strong AR. I'll use AR for atmospheric river. On the right, you see the zoomed in precipitation field from the National Weather Service of 24-hour precip, and there are totals in there of 6 to 8 inches in 24 hours. And you can see the close alignment between the strip of heaviest rain and the AR. This is sort of an iconic result. It's not exactly that perfect every time, but this is statistically essentially what happens. In other words, to get the heavy precip right, you've got to get the atmospheric river right on the West Coast, and anywhere else the ARs are important. As I'll show you one slide later, ARs are a thing on the East Coast as well. Embedded in nor'easters is often a supercharged AR, and the details of where that is and how it is, especially in the initial condition over the Gulf, is also important in determining the details of the impacts here. Oops, went backwards. There we go. So here's one of the key new data sets in the middle on the right is the satellite image from SSMI, and it shows the integrated water vapor in the atmosphere. The band at the bottom is the tropics, tropical, and then the atmospheric river is highlighted there. Imagine that along that band of high water vapor content is where the winds are sort of parallel to that, more or less. It's not always true, but it's literally pushing that water vapor along at incredible rates. If you slice across an average AR and calculate the flow of water vapor, an AR is typically about 500 kilometers wide, a couple thousand kilometers long. Sometimes they're curved, sometimes they're short. If you slice across one, though, on average, there's so much water vapor transport, it's the equivalent of 25 Mississippi rivers worth of water that discharge into the Gulf, or 2.6 Amazons. They're literally the biggest rivers of fresh water on Earth, but they're rivers of vapor blown by the wind. And they contribute substantially to the total flooding in the West and in other parts of the world where they're a primary thing. They also do so there, and they also produce much of the beneficial water supply. Based on public interest and need to distinguish whether an incoming AR was going to be strong or not, we developed a scale at their request, with stimulus from the public and also National Weather Service folks. So I led the team of 8 of us, including 2 Weather Service forecasters, to develop the scale. And what you see on the left here is a little schematic. A key attribute of this is that it applies to a point and the time series of what's happened or is happening or going to happen at that point. How will the integrated vapor transporter, I'll use IVT, behave as the storm approaches and goes overhead? So you want to know when the AR starts and when it ends, because the duration is important. We all know just by intuition that the longer a storm lasts overhead, the heavier the precip could be, the storm total. And then also during the storm, what's the strongest IVT during the period the AR is overhead? That tells you the rate during an hour or two kind of thing. So an average AR lasts about 24 hours on the West Coast. And what you see here is we develop the scale from 1 to 5 based on if it's 24 to 48 hours long and it's over this threshold of 250 units of IVT, and below 500, that's a 1. Go up another 250, that's a 2, 3, 4, 5. Or if the AR stalls and lasts more than 48 hours, we promote the ranking by 1. If it moves through quickly, we demote it by 1. And that's the basic idea, to build in the duration and the intensity. We did not calibrate that with damages, but afterwards, colleague Tom Corningham worked with us to develop a catalog. We have a catalog over 40 years of AR events, and all the flood damages from FEMA over 40 years in the Western U.S. were used as a basis for this diagram on the right. And that's a logarithmic scale. So basically, you ramp up on the amplitude of the strength on the ranking on the AR scale, and you end up with higher damages on average. But notice the dots at the top and at the bottom. There's huge range of variability from case to case. One reason, if the AR hits a super dry environment, like in the beginning of the winter, there's not going to be that much runoff. Damages are going to be muted. If it doesn't hit an area that's vulnerable, maybe there's not much built infrastructure, it's not going to be very damaging. So you should expect wide range of differences there. We've developed a set of tools at CW3E because a lot of people want to know what's going on in these storms and what's coming. And there's a whole audience for that, decision makers, the public, the media, et cetera. So we've invented tools like this on the diagram. On the left is a mapping. The dots on the coast represent the maximum AR ranking in the next week. In this case, it is the GEFS forecast. And you see the red dots there. We're in AR5, which is quite unusual. Hitting the Bay Area in 2021, happened to hit on a Sunday night during a Sunday night football game. And it was literally, they showed that a loop of this and explained it on Sunday night football at the beginning of the game. It was a super surprising thing. And on the right, what you see is 14 days, and in the vertical axis, the IVT for that site. And the middle, to the left of the middle, is the past 7 days. So you see what happened. On the right is the forecast, and you can see a range of possibilities there. That's the ensemble. And you see the big AR5 hitting there at that time. And the width of the vertical band of color is the duration of at least over 250 units. And the color is according to what the AR ranking is for that event. And what you see here is also a family of ARs sort of hitting together, and that's something that can take one AR and make it even more impactful. Another thing I want to highlight is the emerging awareness in our leadership in our community of the importance of water cycle extremes. This was a report from the OSTP, the White House Office of Science and Technology Policy, on Earth System Predictability Research and Development, a Strategic Framework and Roadmap, published in 2020. during the first Trump administration. And the executive summary, literally that text box you can't read at the top, has its punchline statement. The goal of this R&D is to attain high-resolution predictions and projections of high-impact water cycle events, their cascading impacts across the Earth system, and their coupling to human, ecological, and biogeochemical systems. Cascading impacts include things such as droughts, floods, hurricanes, extratropical cyclones, atmospheric rivers, and wildfires. The entirety of this whole major report emphasizes water cycle as the common theme to make sure that we do the best we can to understand and predict those. Changing gear now to prediction and atmospheric river reconnaissance. First of all, let's take a look at our amazing accomplishment of modern weather prediction. The skill score for 500 millibar height anomaly correlation coefficient has climbed from the 80s at about 0.5 to roughly 0.9. Those forecasts are amazing. Even at 5 days lead time, this is for. But what's missing is the fact that we don't get the precipitation right as much as we should. This is sort of schematically shown on the same scale, although the parameter is actually different. This is the equitable threat score versus the 500 millibar height anomaly correlation coefficient. The point being is the skill score is very low for strong, heavy precipitation. We all know this in our personal lives. It's gotten better for sure, but look at the incredibly slow rate of improvement there. The different colors are for different lead times. At 3 days lead time, even the skill's at like 0.2. So something's going on here, right? Getting the large scale right is a necessary but not sufficient condition to get the precipitation right. And this requires looking at things differently. That picture with the purple in it and the streamlines, you could see the AR well displaced from the cyclone. That's like a hint about, yeah, we need to be looking at the storm itself. You can't get the extreme precip right unless you get the storm that produces it right. I think we've spent too much time in our field looking at trying to figure out how to make the correlations between the prediction of a two-dimensional field right compared to what's observed. What we need to do is get the structure of the storm right, the intensity of it right, and the timing of it right. All those things are going to determine that two-dimensional field on the ground. And you cannot get that two-dimensional field right unless you get all those things about the storm right. That's where our focus, my focus, has been in our center's development and in much of my work in program management, et cetera. All right, what have we done at CW3 to improve precipitation forecast, really laser focused on the West and on ARs, in particular the cool season? We have developed a weather model tailored to AR prediction. We call it West WRF, the WRF, the Weather Research and Forecast Model. We have our own supercomputer dedicated to this at the San Diego Supercomputer Center as a partnership. We also have decision support tools on the bottom left there. You see a diagram I won't bother explaining here, but it looks out 16 days with ensembles. We have underlying precipitation science and atmospheric river science. We use artificial intelligence, and we lead the development and collection of new observations, in this case, AR Recon, which I'll dive into in just a moment. Some skill scores from our West WRF model, which has been about 10 years in development now. This is from a publication, Gazvinian et al., 2024. And both diagrams are essentially the same. I'll just tell you about the left one, which is the Breyer skill score for greater than 1 inch or 25 millimeters of rain in 24 hours. And the vertical, higher is better. And the blue line is the GEFS ensemble forecast system. The green line is the ECMWF. And look at those red and purple lines. Those are our center's model is beating the pants off ECMWF and GFS in ensemble prediction of heavy precipitation. And we go to a heavier threshold on the right, and we see that as true still. And we have the purple line is above the red line because we use machine learning on top of the ensemble products from our West WRF model. I'll also highlight that using machine learning it was the focus of Will Chapman's Ph.D. under me recently, and this award-winning paper showed that by using a post-processing method, it was possible to increase the skill or reduce the error, the RMS error. The left-hand diagram, the vertical axis is RMS error, horizontal axis is lead time, and the basic thing to compare is the purple and red lines. The red is the GFS raw, and the purple is GFS with the machine learning applied. And we reduced the error at 7 days lead time by it's at several days lead time by 20% just by doing that post-processing. And now we've introduced our first machine learning forecast product, illustrated on the right there on our website. The main headline on our work, though, I think from the observation standpoint, is atmospheric river reconnaissance. When I was in NOAA in 1998, I led a field program off the West Coast, and it became crystal clear that we needed to know more detail about what's going on over the ocean before these storms hit than we had normally available from satellite or buoys. And even as satellites have advanced, there remain serious gaps. The measurements critical to AR prediction are the water vapor content, the temperature, and the winds in the lowest 10,000 feet of the atmosphere in a fairly narrow region, often blocked by high-level clouds because it's an area of moisture. So any of the visible sensors are having a problem. We don't really get the low-level cloud-tracked winds in ARs, largely because, even though that's where it matters, because we've got high clouds in a lot of the areas to block it. With the microwave measurements that can get through the clouds, those tend to be areas where the error characteristics of the remote sensing measurements are much higher. There's larger error in those measurements, and those thus degrade the ability of assimilating them to improve the model forecast. And I'll come back to that in just a minute. So we take the U.S.'s arsenal of weather reconnaissance aircraft from NOAA and the Air Force, and we deploy them now in the winter. We started this 10 years ago this year, and with a demonstration, Vijay Talapragada, I'm the PI and leader, and Vijay is co-PI as the leader of the GFS and senior scientist at NCEP. And we have worked on this together for a decade. And we have shown here in schematic that slug-like feature, translucent with the orange in it. That's the AR. Point being shallow and relatively small and offshore. Narrow. And the drop-sons are our main tool. But we also have what we call airborne radio occultation, which is led by Professor Jennifer Haas at Scripps, and it sees the satellite, GPS satellite sunrise, sets and rise from the aircraft, and that allows the plane to look out to the sides essentially, while the drop-sons go in straight down. We also supplement global drifting buoys that are deployed for sea surface temperature and ocean surface currents. My program and yours truly, we add barometers to a bunch of them. So for like 60 of them a year, we put out. Our center now is responsible for like 13% of the global measurements of sea level pressure from the drifting buoys around the globe. And they are helping with that measurement as well. And there's other things we're doing also, but on the bottom left, you don't see too much of it, but we have dozens upon dozens of papers. This is a hardcore scientific program in addition to an operational program. We went operational in 2020 as it was incorporated into the National Winter Season Operations Plan. We've now since then conducted over 200 aircraft flights in these last few years. And I'll share in a moment something we call the Global Atmospheric River Reconnaissance Program Demonstration 2026, which we just completed a few weeks ago with colleagues from NASA and Europe, sort of partnering with us, with the foundation being AR Recon. In addition to the AR itself, which we know is the primary reason, there's a whole slew of papers on where the targets, why this is a key area, but it's really common sense. Latent heating is one of the primary drivers of the evolution of the weather. And if you don't get the latent heating right, you're going to have a hard time getting the forecast right. What do you have to do first order to get the latent heating right? You have to know where the water vapor is. And the AR is essentially a flow of water vapor into a cyclone that can go up the warm conveyor belt, and then with the upper level dynamics supporting all that, including the jet streaks and jet stream aloft, all and the ageostrophic circulations of that, which by the way is what really got me into meteorology. I just love that stuff. Beautiful mathematics, elegant, really conceptually informative. And now we know about potential vorticity and all that. But if you don't get that water vapor right in the initial condition and the wind that's pushing it along, how can we expect to get the late heating right later? So that, I think, is the underlying major reason that we see the AR as such a driver of forecast error growth. But what controls the AR includes the PV aloft. It includes the ageostrophic circulations from jets. It includes the front. It includes the cyclone itself. So each of those we consider essential atmospheric structures. I don't need a computer or a mathematical tool to tell me that. It's super intuitive. So we've built AR Recon around an approach that has both objective mathematical tools for targeting that are super cool math and very helpful, but they tend to look pretty noisy. When we've compared them with the essential atmospheric structures over the decade of now working on this, they've refined their targeting calculations, and they're coming more and more into line of what we knew from day one to be the key approaches, the essential structures. So this is really fundamental to our whole program. We have daily briefings where we have a mission director who's in charge of deciding whether to fly or not and where to fly, a team of forecasters, a team of other experts who we have discussion every day about these essential structures, about what the mathematical tools are showing and what the importance of a particular event is. And then the mission director makes a call about where to fly and if and where to fly, all with, of course, close consultation with the aircraft flight directors who have safety and facility availability in mind. And this diagram on the left, picture on the left, just shows my office with representative from ECMWF, from NCEP, from NCAR, from my group, and others talking. That's sort of the message of how we work. We have a more formal structure for the meetings, but we call this a research and operations partnership because the flights are called not solely for the operational benefit, but in addition to help advance the science and test hypotheses. And the feedback between those is a beautiful thing. We also coordinate this and drive it by in a fashion or motivated by Forecast-Informed Reservoir Operations. And we have a RAOP approach to that as well, Research and Operations Partnership. This is what we flew over the last couple of years. Each of the blue dots is the NOAA G4, and the red dots are the Air Force C-130s. And you can see sort of the numbers in terms of dropsons. You see some over the Pacific, over the West Pacific as we're expanding. You see some in the Gulf and off the East Coast as well. The bottom panel is from this season alone. And one of the impact slides we have, and there's a number of papers on this. This is from Lord et al. 2024, and Talapergata et al. This year came out, and there's other papers from ECMWF and on the Navy for NOGAPS and from West Wharf. And the main thing I want to point out is those tall bars on the right. California domain is where we verified. This is the percent improvement in estimated skill for different thresholds of precipitation. 72-hour forecast. The green and the orange, or the green and the gold, are the higher precip thresholds. And what you see is on the order of 10% improvement over an entire season on the West Coast for this. That's what AR Recon has been trying to improve, and that's like a whole decade nearly of model improvement worth of forecast skill improvement on the phenomena that matters the most in the region. There's also, I won't go into the details because I'm out of time, but an anchoring effect. You put in situ measurements in a cloudy and precipitating environment, a data assimilation system, which might struggle to fully utilize the remote sensed microwave measurements, is better able to utilize that remote sensing measurement because the model, the DA, knows what truth is at that point, close enough that it can zoom in or somehow, I don't know the math of it, but it can somehow know better how to distribute the information from the remote sensing, because often the vertical source positions are uncertain. So we get up to 5 to 10% increase in use of satellite data in the actual assimilation step when there's this when the dropson data are available. It's called the anchoring effect. Also mention that because water is king in the West and forecasts of precipitation and storms in general are super important to the nation, our leadership, both Democrat and Republican, have gotten behind this program of AR Recon. And a bill was passed that was introduced by Senator Padilla in 2023 called the Atmospheric River Reconnaissance Observations and Warnings Act. And it was signed into law after passing the Senate and the House in 2023 by Biden. And it describes the basis for the recommended growth of AR Recon to include the West Pacific and the Gulf and the Atlantic, as well as the use of the RAOP approach to ensure its continual improvement in outcomes. That has grown now to launch what I dreamt up about 10 years ago, and 5 years ago finally daylighted a bit, and now it actually happened. This last winter, we spent a month flying. On this map, you see the West Pacific. We didn't get that one done because of the government shutdown, frankly. But we flew out of Hawaii, we flew out of California, we flew out of the Gulf into the Gulf out of Biloxi and out of Florida, and also worked with the NASA's Nurture Field Campaign, flew out of Canada. They cooperated with us, and the Nautic Field Campaign out of Europe also did. And we flew this mission, the first ever IOP of the Global AR Recon Program, or GARP, happened in late January during AMS, and or just before, and was a major success with over 10 flights in that period and tons of data collected. This is what we collected over the 30-day period of GARP demo 2026, and you can see the colors correspond to different dates, but the remarkable array of 72 flights, over 1,100 drop sounds. We also had 175 of those drifting buoys instrumented with sea level pressure sensors, including the Europeans matching what I did in the Pacific. We also had extra radiosondes launched from universities around the country. I dreamt this program up out of interest in increasing the education opportunities for people to get involved. So any university that has a radiosonde system as part of their training program for teaching meteorology, we got feedback that 25 of them around the country would be interested. If I could send them the radiosondes themselves and the balloons, they would bring the helium and the students, and they would launch during the same times that we're flying the AR Recon missions. Last year, we did 5 stations like that out of philanthropic support. This year, out of my reservoir operations work funding, I dedicated enough to cover 16 stations around the country. And as part of GARP, the European community also brought some university radiosondes to bear, and we're now planning to do GARP Demo 2027 next year, including more radiosondes even than this. As you can see, 150 students across the 16 universities participated, and thus are learning about the value of data collection, the value of the observations, how a global effort across countries can help improve forecasts for all of us, we hope. I'll turn to FIRO now. And very briefly, what is FIRO? It's a reservoir operation strategy that better informs decisions to retain or release water by integrating additional flexibility in operation policies and rules with enhanced monitoring and improved weather and water forecasts. This is published in the American Meteorological Society 2020. The Army Corps of Engineers, USACE, FIRO program is something that we developed over the last 10 years or so. It's managed by Dr. Carrie Talbot in the Corps of Engineers, and I'm the chief scientist. And you see a picture of Lake Oroville in California, one of the biggest dams in the state. The key emphasis being that in the winter, and this is like 2.5 years of data on the left for one reservoir in Northern California, map on the right. The orange line is the level the water is supposed to be kept at different times of the season, partially empty during the winter for flood control, then filling in the spring. But we don't always get enough rain in the spring to fill it. And what we see happening in the middle here is a year where big storms, 2 ARs came in back to back, filled half the flood pool, and the reservoir operators, by the rules that are in place for good reason at the time, had to release that extra water down to the orange line right in the middle of the diagram. But then notice there was no chance to refill it because Mother Nature didn't produce the inflow. And that dropped it into the lowest record low water level a year later. And this became a political issue as well as a practical one. And the challenge is, could we actually have saved some of that water from those storms the previous year? And this is where we've developed all the tools and methods to test that. The bottom line is, imagine you're here in the middle of this one right here, and your like normal rule says release it all. What if we could keep part of that for another day? And if there's no forecast of another big storm, keep it for another day and go forward through the season until spring when the flood risk is over. And maybe you've got more water in the reservoir by then. Well, how do you know you've got enough lead time to do that safely? Depends on the geometry of the system. So the reservoir here is 74 miles to the flood-prone spot downstream. That's like 2 days of travel time for the water once it's released from the dam. If we did 10,000 acre-feet of water, which is enough for like 20 or 30,000 households for a year, which is a lot, that would take about 2 days to release from the reservoir using their outlet structure. So it's about 3 to 5 days lead time. If we could see, and ARs are the only storm that makes floods here. So if we could see an AR storm coming or not with reliability, the forecast could help inform the reservoir operator to say, oh yeah, I'll keep that water for another day with confidence it'll work out. I won't get into worse trouble with a flood, unexpected storm. And we've now done this for 7 years. And it's worked every year, whether it's a flood year or a drought year. By the end of the year, there's like 10,000 acre feet more water available for the public and for agriculture. That is a huge economic impact. And this is our pilot study. We're now working on several other reservoirs in California, 14 more in the Northwest. We've done a screening assessment nationally. We think there are at least 100 other dams that look super promising around the country, all over the country, including in the East Coast, for our program, and we're heading in that direction. I'm going to skip over this. This just shows what I said verbally a second ago. One of the reasons that it works in the West is because ARs are more predictable in terms of extreme precip than other storm types. Tropical storms and convection are harder to get the precip right in. And this is analysis from Cordera et al., 2025, Weather and Forecasting. The blue colors are good forecast skill. The tans are not so good. And what you see on the West Coast are these incredibly deep blue colors. That's because those are the best forecasts in the country for the top 5% wettest days in a 20-year period at day one lead time, just as an example of the measure of variability of skill across the country. Interestingly, you see the Great Plains is very low forecast skill. These numbers are really lousy forecast skill for extreme precip a day out. And it's convection. We all know that as meteorologists is super tough. But interestingly, look at New England, even this area. We have some really good skill there. That's because, frankly, atmospheric rivers are part of the storms here. You know, like I mentioned in the nor'easters, here's 3 examples. This is courtesy of Jay Cordera, part of our center, and he's based at SUNY Albany. And the gray area there in the middle is super strong AR IVT, over 1,200 units. So these are very, very intense ARs, and where the details of where that hits and how long will impact the snow and the rain and the flooding that affects the East Coast. You know how often is the case that a 50 or 100 miles difference in the track of a cyclone, a nor'easter, makes to the impacts? Remember that thing about AR Recon? If you don't get the water vapor right and the AR right in the initial condition, it's hard to get the storm right. It turns out that if a cyclone is just beginning to form and it has an AR already nearby, it's on average going to deepen 50% faster because it's supercharged by latent heating. It's that simple. So if you don't get the AR right in the initial case, you're not going to get the cyclone right. If you're not going to get the cyclone right, it might not get the nor'easter right. So we're just at the cusp scientifically of pursuing this as a technical analysis, and I'm really hopeful we'll be able to show it. The public's been very interested in this. Scientific American asked me to write an article. So if you want a common language summary that connects all these things, AR Recon, the drought, flood stuff, the ARs, you can find it in this article from a couple of years ago. And that was their diagram. They had all control over the graphics. It's a little over dramatic for me, but it's nicely done. They did give me one thing I could edit. They had lightning in that. And I'm like, it's not really lightning, you guys. Could you take that out? They did. But I think it's still pretty cool artistically. All right, final section. How am I doing on time? 41? Okay, I'll whip through these. This one in particular, I'm going to just jump through. The boundary layer under ARs, the punchline is that it's a stable boundary layer. Here's a big AR we sampled here. These are 3 flight tracks for the same storm. This is a dropsonde from this point. In the lowest 1,000 meters, what you see is very stable air. This is theta, warmer than the SST. And you see vertical wind shear very strong. Well, because it's stable and the ARs are associated with the low-level jet aloft, which can be hurricane intensity in some cases. And the water vapor flux, of course, increases with that wind speed. And the Richardson number is subcritical, so turbulence is present below 600 meters. This is the AR boundary layer above the ocean. It's a stable boundary layer. It's a tough thing to get right. And yet it varies dramatically from storm to storm. If you look at this as a diagram, it looks like a bit of a platypus to me in the black, but here's that dropsonde. If you back trajectory at 24 hours, it started over here in much warmer water. By the time in 24 hours it had moved 1,700 kilometers, the ocean under it had cooled by 13 degrees C. So that AR is pumping sensible heat into the ocean. And that's why it's a stable boundary layer. It's losing heat, so it's stabilizing. And it turns out our study here with 99 cases shows that on average it's about 600 meters deep, but that it varies dramatically from storm to storm. Because imagine the AR isn't aligned so that the back trajectory goes south to north. What if instead it goes west to east along the SST gradient? So this solved a mystery I had puzzled over for a decade. I had the hypothesis back then is that when we have a trajectory of an AR where these back trajectories come south to north, you get a lot of sensible heat loss. And that's what these cases on the left designate. And when the AR instead is parallel, you don't get much sensible heat loss. The red and blue coloring are how much vertical shear there is. There's very little vertical shear in the red ones, strong vertical shear in the blue ones. And there's an intermediate case. It's a bit of a mix. Under the strong ones, where there's lots of crossing of SST gradient, you see super strong downward sensible heat flux. That's the color fill. The black lines, IVT. This is a composite of many cases. So what we see is literally the correspondence between downward sensible heat flux and the presence of an AR. It's that simple. And when you don't have an AR, you still get some, but it's a little bit disorganized and not nearly as strong. There's some other things. You can find the schematic in there. We looked at a long AR variability and all, so you can see that just because I'm out of time. I want to hit a few more items. Oh, and that paper is in 2024. Where's the paper citation? I don't even think I have it in here. Monthly Weather Review 2024. Very recent paper, just this last month or two, is by Marty Webb and a few of us, and it shows how soil moisture. Remember the AR's ranking, the dots for the economic impacts were sort of wide ranging outside the median. It's because of this. If the soil moisture is really dry, you're going to lose a lot of the potential to increase the stream flow because it goes into the soil first. You can see that schematically. So we've been, Marty Webb led this, and it's really an elegant expansion of the AR scale or refinement of it to bring in another way to elevate or to promote or demote the ranking based on whether there's strong soil moisture, wet soils or dry soils. And you can read this afterwards for clarity. And in 70,000 events over 142 watersheds, it nearly doubles the correspondence of the AR ranking with the stream flow. We knew when we created the scale that soil moisture was important, but we had 10 other parameters that were also important. We decided to focus on the storm itself and allow for consideration of antecedent conditions, of vulnerability of infrastructure and all that to then help define the actual impact. Next is the ocean. Little complicated diagram. This is several days in January. It's a paper by Giglio et al., 2025 in GRL. The previous one was in Nature Communications. And this is using autonomous floats underwater, Argo floats, to sample the salinity changes in the upper ocean when ARs go overhead. Turns out between Hawaii and the West Coast, ARs account for like 80 to 90% of the rain on the ocean in the winter. And therefore they act to change the salinity. And what you see here is that salinity change is seen as deep as 25 meters. It can last, better part of a day. And the dotted lines here, which you can't see very well, are what the models think should be happening. And the solid lines are what the Argo float actually saw. So there's some problems with the model that need to be looked at. The salinity is obviously a very important thing in oceanography. Polar regions. ARs are vital in polar regions. Half of the water vapor above the Arctic Circle gets there in the form of ARs transporting it laterally through either near Greenland and the gap, between around Iceland or west of Alaska. 50% of the water vapor in the Arctic. You know what the heating in the Arctic is coming from a lot is the water vapor and the loss of ice. It also turns out that when the ARs go overhead the ice, they transmit huge amounts of sensible heat downward and also not sensible heat, radiative heat, because they're warm, wet clouds above, and they have a major role to play in Arctic ice melt. Now, they also bring the high winds that help physically break up the ice. This is Antarctica, believe it or not. These are two beautiful papers by Jerry Zhu in my group, and they resonate with a nice paper by Wiley et al. In 2022 about a major heat wave in Antarctica. And what we see here is during the big heat waves, during a big heat wave in Antarctica that was studied by Wiley et al., we saw AR was corresponding to that. This is actually about the changes in the ice. I'm running out of time, so I'm going to jump ahead. We've got an enhancement to the AR scale to allow for polar region application. I've highlighted in the lower right. This is in a paper by Zhang et al. Just a year or so ago. That's some stats. These are thresholds that we've calibrated to how often they occur in the Antarctic and Arctic, particularly Greenland, and they're in the lowest few, just a few percent of days have this kind of magnitude of IVT in that climate. This is really the final slide, scientific slide, is that on the right side, what you see is a red blob over Antarctica. That was a heat wave that produced a high temperature, 77 degrees Fahrenheit above average for that date. Let that sink in, 77 degrees Fahrenheit. It set the all-time record high for that location in one of the coldest places on Earth. And it did it in a way that would be analogous to saying College Park set its highest temperature on record in December for any day of the year. That's how anomalous it was. And guess what? It was fed by an extremely anomalous AR, transporting not only the moisture, but also the sensible heat. The diagram on the left is the duration of AR conditions associated with the IVT. And in this case, we time integrate the IVT, that's the vertical axis, and look at how much of an outlier the time integrated vapor transport was for that case over Antarctica that was so anomalous. I'm not an alarmist by my nature, but I am a pragmatist. And on the west coast of the US, if we had an AR that was this anomalous from what we've seen in the last decades, the impacts would be pretty substantial. I think they would be here as well. So the fact Mother Nature could produce this, it's a remote place that none of us live in, it's hard to relate to. There's something going on. There's something new in the world that's happening in our era anyways. I'm sure go back millions of years, many things have happened. But this is clearly related. The main point here is that not only did it cause a lot of melt, but it deposited 300 gigatons of snow. ARs are one of the major contributors not only to melt in Antarctica and breakup of ice sheets or ice shelves, but also to snow accumulation. So they both give and take away. Uncertainty in the future of ARs in our polar regions maps straight on to uncertainty in our climate in a much bigger way and into global sea level. Finally, I'll close with I started 10 years ago now almost, an international AR conference. We get about 150 people join each year. This year coming up, October, come to Porto, Portugal, and join us for a great week-long interaction, very interdisciplinary across the sciences and across the science and applications. And would love to have you. There's a website for it. You can just search IARC and find it. And I want to give credit to the many people in my group who did a lot of the work I presented here and have developed their careers. Many of them are early career, working towards these very pragmatic things with an underlying scientific foundation. We have a few visitors you might recognize in the group there. This is from Scripps Oceanography. And I just really want to thank everybody who's sponsored us and who has been part of our program and collaborated with us over the years. And welcome any questions you might have. Thank you.
Okay, so we can take turns between in-person and online. Online people can just type their question in the chat, and in-person can just wave me down.
Thanks very much, Marty. Fascinating stuff. I have a question about the observations. So I was very pleased to hear you mention the need for getting the geostrophic flow right. This is a battle that I had been fighting for a couple of decades, and I was fighting for the radio sound observations when I was in WMO. They still have, on a per op basis, the biggest impact, not on the stuff that you were talking about, but even on the very standard metrics, anomaly correlation coefficients, and RMS errors in the tropics. But they are unloved for two reasons. They don't have a lobby behind them like the satellite systems do, and the environmentalists don't like them. You will have the same problem with the drop zones. They cost money, not huge amounts of money, but you have to pay for the flight. There's no strong lobby behind it. And it's not a huge garbage problem, but conceptually it's wrong to litter the environment with disposable instruments. And there are people who really don't like it. Where do we go? Do you have any other observing systems in your back pocket that can help with this? It must have been something that you've been thinking about.
Oh, it's come up occasionally. And when you look at the real numbers, it's not that big an issue, and most of the material is, biodegradable. So it's come up a handful of times, but not that much. And the radiosonde system is very interesting. There's a whole community now that goes out and tries to track them and find them. And it's like a trophy for them. And so that's a really interesting thing in its own right. I want to emphasize on the observations, though, a really important thing I've come to believe and have pursued. First of all, there are advocates for all of this, and they are activated through our water work to be advocates, because to them, if we've got good methods that could be applied that aren't super expensive or have other real bad things, we should be doing that. We shouldn't be fighting with each other over which one's best or cheapest or whatever. If we add more measurements, we're going to get better forecasts. Not willy-nilly. There's got to be some, reasonable assessment of that. So I've come to believe that rather than taking the either or philosophy of it's going to be either this system or that system, say satellite versus in situ, it's and. Neither can do it all, but combined, we can make the forecast better. And when you look at the cost of what it takes for us to do the and, relative to the benefit of better prediction, particularly in water, it's pennies on the dollar. And the people who care about water, they are now going to bat for our field to make sure that politicians and other leaders know this is the case. We sort of look like we don't really understand how important our own work is when we fight each other over what the top priority is. We need to prioritize. It's always a thing. The zero-sum game argument is always there. We're always careful about budget. But the reality is the benefits of what we do as a field are so profound. It's also true that we could make a better case for that, and therefore for greater investment in what we do.
Quick reminder, for all our online people, please type your question in the chat. So I think.
Thanks, Ralph. I'm Tavakoli from Erdik. Good to see you here.
See you too.
Two questions regarding FIRO that you mentioned. Just wanted to, if you could, maybe just mention a couple of sentences about the plan for future for FIRO, but also for the forecasting. Maybe I didn't catch it. Are you using ECMWF forecasting or the National Water Center forecasting, like HERP forecasting?
Yeah. So the National Weather Service GFS forecast system is really a pillar, and GEFS. Our center brings also ECMWF data in. I think I mentioned we have a 200-member ensemble of West Wharf. Those members are informed by either boundary conditions from ECMWF or NCEP. We also torque the parameterization assumptions and some other, there's a SCEBS thing. I don't know what I'm even saying, but apparently it's a thing in ensemble generation. So it really integrates all of that and to produce products that are being considered in decision-making in the couple of reservoirs that we're using it officially now. And the future, you asked about that a little bit more. So because we started FIRO in the West, where ARs are more predictable. We had a better chance of making it, see if it could work. I sort of anticipated it would be the best place to start, and it was. So the question now is, well, where else in the country are ARs important? And I showed the example of New England and the East Coast. So there may be some opportunity there as well, and in other parts of the world, frankly, but also tropical storms and convection. I think this FIRO work lays out a gauntlet for our field to work to improve the precipitation, the forecast of extreme precipitation from all storm types. But like I said at one point, remember, it's not a two-dimensional field. We have to get the storm itself right. So in the case of ARs, we've made a lot of progress. Hurricanes, there's been a lot of progress in getting the deepening right and all that, but maybe a laser focus on the precipitation part of it is needed. Convection we got to work on everything. And we're not starting from zero. All of these have some promising, hints as to what direction to go, and some very innovative investigators and scientists and forecasters working on it, but there's a lot more work to be done.
Chat question: is it possible to provide the shapefile / raster download from your site of the AR forecasts alongside the PDFs? Varying timescales from the 7 days would also be of interest.
That's over my head, but happy to receive an email request for the details, and I'll pass it along.
A quick comment and a question. So first of all, I've been collaborating with people in Newfoundland and Labrador looking at carbon fluxes from landscapes, and the atmospheric rivers have been hitting Newfoundland and Labrador, are now generating the biggest dissolved organic carbon fluxes, therefore decreasing the carbon storage up in those.
Oh, wow.
Yeah, and that's the boreal forest. That's the carbon storage reservoir. So this is a big part of, we just had a paper that we submitted about this to soil scientists, basically. But yeah, the AR is really important up there as well. The question is, I don't quite understand the mechanisms that trigger the AR development in the tropics in the first place. Can you pinpoint where an AR is going to develop and why, or do you just see it starting to initiate and then say, okay, we're going to track it?
Yeah, there are indicators, and ARs can start, and in the mid-latitudes, they don't have to be, some have a tropical connection, some don't. One thing, we did a study some time ago, there was a big case that hit Oregon, and we had flown out of Hawaii, so we dug into that deeply. And by the way, the big case in Oregon hit at the end of a drought. And I happened to talk to I had a visitor that day from, or afterwards, as I was talking about this case, from the senator's office from Oregon. They had just convened a drought meeting with the community leaders on the day it poured rain. So they were very sensitized to how ironic that was. That storm actually had a tropical tap, and it was possible to tap the tropics partly because there was a Kelvin wave in the tropics that had displaced the northern edge of the very moist air of the tropics poleward a bit, so that when the extratropical features dug far enough south, they converged and ended up merging into a very strong AR. There's something called a tropical moisture export, which is another mechanism that can do that. And we did, and we have a chief editor of a book, the book on AR, Atmospheric Rivers, Springer 2020. And we had 34 contributing authors, 8 chapters. And one of the chapters was about the relationship between atmospheric rivers, the warm conveyor belt, and tropical moisture exports. And they have some common DNA, like the Venn diagram. There's definitely some overlap, but there's also very important differences. Not every AR has a tropical moisture export that it taps into. Not every warm conveyor belt has an AR feeding into it, that sort of thing. So really good question. Thanks.
Thank you. It is 1:02, so a couple minutes after our hour. So I just want to give a big thank you to our speaker, Dr. Marty Ralph. And thank you to everybody for coming.
Thank you. Thanks for the opportunity.
Have a good afternoon, everyone.